Good morning. Our project is RFID, Biomedical Information System, with passive sensor tags. My name is Salman Nakvi, and my group partners are?
My name is Phong Pham.
We are especially thankful to our special sponsors, RFID Sensor Systems and New Jersey Microsystems, and our project was partially funded by NSF. Our goal was to enhance the farm animals biomedical information system, and we used the radio frequency identification technology using passive tags. Passive tags are the RFID tags which do not contain a battery, and they are energized by the reader's power and reader signal interrogating the tag. Our goal was to provide the full accessibility to the farmer, which would be the main user, of all the biomedical information that our sensors take. Our inspiration came from the United States Department of Agriculture's initiative to set up an electronic farm animal management system to enhance the disease traceability.
Motivated by this information, we approached the project by utilizing the available hardware at New Jersey microsystems such as the patented far-field RFID passive tags. Our embedding sensor systems are temperature sensor, which tell us the temperature of the animal, and the strain sensor, which tell us the weight of the animal. This helps the farmers to be aware of the animal's health condition. And in addition to that, we also developed a graphical user interface, GUI. We prefer LabVIEW to other development environments because of its extensive support for accessing instrumentation hardware. So we did a small comparison. So how our approach unique from other current approach. Current systems only focus on passive tags that are only readable and only for identification purpose, and sensors only embedded into active tags only. So our approach, the first one, embedded sensors into the passive tags, and we proved that our long-range readability of passive tags to be 300% enhancement over the current systems, and by the friendly user interface from LabVIEW, farmers has full control of the system.
So before we explore our approach further, let's look at a brief overview of how a simple RFID system looks like or works. So the main node in the system is the RFID reader. It is connected to a host computer. A user can access this RFID reader using a GUI interface, which we created with LabVIEW. He sends the command, so the user has the full control of sending the commands to the RFID reader. Once the command is received, the activation energy to charge the passive tags, which Salman is actually handing out, which you can take a look at, is charged, and in response returns the data stored in it. So in our case, we had RFID passive tags with a temperature sensor and a strain sensor, so it would return the strain or the temperature value. So the following slides would discuss the methodology, the algorithm, the block diagrams that we used to create this whole project or the prototype, and it would discuss the GUI LabVIEW interface, the temperature sensor module, and then the strain sensor module. Since the range covered by the passive tags is crucial to the efficiency of our project, let's take a note of the proof of performance. There were various tests conducted in different environments. There were three: a closed room, open environment, and then an anechoic chamber. And the results were as shown above. The range was between 50 and 150 feet. That is over 300% improvement compared to the current market's passive tags. The Star Ledger actually substantiates our results by printing standard cattle ear tags on the market have a transmission distance of just 5 or 6 feet, while his NJM is our sponsor, which provided us with the passive tags, work up to 50 feet.
Okay, so our LabVIEW coding can be summarized in this command flow diagram. It involved 4 major stages. The first stage was the activation of the tag by the reader. LabVIEW would send the command to the reader to activate the tag. The tag, or the sensor connected to the tag, would start collecting the data, which would have a measurement delay time. After that, the data is received by the LabVIEW. It is parsed and manipulated to be displayed onto the screen. Here you can see the GUI interface that we formed for the farmer. This particular screen for the search purpose, the farmer can include the EPC code, which is a unique identification code for any passive tag, and search the tags in range, or you can just search all the animal tags in range. And once that second option is pressed, the second screen will appear where all the EPC codes of the tags in range would appear, and the corresponding animal IDs, which are stored in the user memory of the tag, would also appear. The farmer can select any of the EPC code and also see that the temperature tag is associated with it.
So both sensor systems share the same signal processor, which is from Texas Instruments MSP 430F2013 microcontroller. And we use the SPI interface as the mainstream communication bus, and the assembly language program is programmed in this sensor system. The temperature sensors is housed in the IDS SL900A controller, and its data ranges from -40 to +110 Celsius degree with the accuracy of ±0.5 Celsius degree. And our strain sensor system is essentially the ACAM Pico strain BS081 chip, and we use the advantage of this system is the extreme low power system module, but still provide high resolution of 24-bit data measurement via the SPI bus.
Alright, so let's take a look at the sensor system flow diagram of how the system works. So there are 5 steps in total. The initiation stage is the RFID sends a signal to the sensor system, which in our case is the strain or the temperature measurement system, and gives it a command to start reading, take measurement. The measurement is taken. Calibration is the compensation of the drifts and the offset. Then we have the data logging. That's only dependent for the temperature sensor, since it's data logging for over an interval and gives you the range. And then the acquisition by the reader. These are the pictures for 2 of the modules. We're set up in the demonstration board in the back, so if you would like to stop by.
So in case of the results, you can see this screen, which is the final LabVIEW screen that the LabVIEW puts out. The temperature data after processing is displayed, and also the strain sensor data is displayed here. Discussion. So our highlight of the experience was using the SPI bus interface to communicate between the microcontroller and the temperature and the strain sensors. We used the TCP/IP port for the data acquisition between LabVIEW and the sensor tags. And we used the block iconic diagram, the programming of the LabVIEW using encapsulated paradigm. Our goal, yes, it was accomplished because we were successfully able to implement the sensor tags.
So the commercialization aspect, at the accomplishment of a project, it is a proof of concept of how a sensor would be embedded into a passive RFID tag and make the system work. So with some future development or improvement in these areas, we could commercialize the project, the product, miniaturizing the sensor system, reducing the power consumption, and stated there.
So we would like to thank the help from and the support from our advisor, Dr. Never, and our sponsor, Dr. Carr and Mr. Brahmakrishnan from New Jersey Microsystem. And at this point, I would like to open the floor for questions. Thank you very much.
Thank you.
Yeah, how did you get the increase of distance by almost a factor of 10?
That's actually a trade secret of the RFID sensor systems. They have the optimized antenna on the passive sensor tags that you can see in there. And they have the patent for it, and they have just started the commercialization of that. And you can see the demonstration.
So have you spoken to anyone in this industry about the solution to get feedback?
Yes, we actually are working with the only